All right, let's talk about something that feels a lot like magic, but, isn't. We're going to look at this one single tool, and you'll be amazed at how it solves problems all over the place, from the words you type every day to the ones and zeros whizzing around inside your computer.
Okay, so picture this. It's something you and I do, I don't know, 100 times a day, right? You pull up a search bar, you start to type, maybe you're looking for something, so you type APP, and bam, before you even finish the word, this list just appears out of nowhere. Apple, application, approve. It's like, how did it know? It seriously feels like it's reading your mind. So how does it do that? I mean, really, how does it sort through a bazillion options that fast to figure out what you're about to type? What's the secret sauce here? Well, that's what we're here to do. Let's pull back the curtain on the so-called magic of autocomplete.
So turns out it's not magic at all. Shocker, I know. It's actually a really, really clever data structure that's built for exactly this job.
And it's called a tree. Yeah, that's T-R-I-E. Some people say try, so you don't confuse it with, a tree. Fun fact, the name actually comes from the word retrieval, and its whole reason for existing, to store a bunch of words so that searching for the beginning of a word, that prefix, like our app, is ridiculously, unbelievably fast.
Okay, so what in the world does one of these things look like? Let's actually build one. Come on, it'll be fun. All right, so first we start with a single empty spot, the root. Now let's add the word app. We just make a little chain. A node for A, which points to a P, which points to another P. Simple enough. But here's where it gets really smart. When we add Apple, we don't make a whole new chain. Nope. We just follow the APP path that's already there, and then right at the end, we add new branches for L and E. See how that works? And it's the exact same deal for approve. It just piggybacks on that APP path before it goes off on its own. And that right there, that's the whole secret. The shared beginnings, the prefixes, are shared paths. That's what makes it so wicked fast and space efficient. If you want to find all the words that start with app, you just walk down that one little path and see where all the different roads lead. Zero wasted time.
Okay, that's pretty cool for words. But what if we could take this same idea and use it for something completely different? I mean, let's jump from language all the way over to pure numbers, to a binary puzzle. So you're probably thinking, can this thing that's so great for letters and words actually handle numbers? Like numbers at their most basic core level? Well, the answer is a big yes. As long as we stop thinking about numbers like 3 or 10 and start thinking about them as strings of ones and zeros. They're binary code. So 3 becomes 0011, 10 becomes 1010. And all of a sudden, hey, those numbers look an awful lot like words, don't they? And this little trick lets us solve a super common coding problem, the maximum XOR challenge. The whole goal is just to look through a list of numbers and find the two that, when you combine them with this operation called XOR, give you the biggest possible value. And the strategy? You guessed it, use a trie. We build it with our binary numbers, and for any number we pick, the trie can instantly find its perfect match, the number in the list that's basically its polar opposite in binary. And here's why that works so beautifully. With XOR, opposites attract. A 1 and a 0 gives you a 1, which is the best you can get for that spot. So if you want the biggest final number, you need to find the number that has the most opposite bits. And our tree, it's like a super fast matchmaker for finding that perfect binary opposite. All right, so we've seen it handle words, we've seen it handle ones and zeros. Now let's get really crazy and combine those ideas to solve a puzzle we all know, but we're going to blow it up to a massive scale.
Yeah, you know this puzzle, the classic word search. It's fun to find a few words, right? But imagine this grid was like 1,000 by 1,000, and you had to find every word from a giant dictionary. How would you even start?
So yeah, that's the problem. Find every single word from the dictionary that you can spell out by hopping from one letter to the next in this grid.
Now, the obvious way, the brute force way, would be to just start at every single letter and try every possible path. But that would take forever. Literally, it would be insanely slow. You'd spend 99.9% of your time chasing paths that just spell out complete nonsense. And this is where our friend the trie comes in to save the day. Here's the hack. First, you dump your entire dictionary into a trie. Then, as you start exploring the grid, with every step you take, you check if that path exists in your trie.
The second you spell something that isn't a prefix to any word in the dictionary, like OAAN, you just stop. You abandon that path completely. This pruning saves a truly mind-boggling amount of work.
Okay, let's just pause for a second and look at what we've done. We've used this one simple idea, the trie, to solve 3 totally different problems: predictive text, a tricky binary puzzle, and a giant word search. That's pretty amazing.
And look, this isn't just for fun and games. This thing is a real workhorse out in the wild. It's what's behind the suggestions on your search engine. It's what helps your phone predict the next word you're going to type. It's even used in things like network routing, helping data find the fastest path across the internet. You'll find it in cybersecurity, in AI, it's everywhere.
And I think that's the coolest part of this whole thing. It's this one simple, elegant idea, just storing things by their shared beginnings. And you can apply it in so many creative ways to solve such different challenges. It just goes to show you, if you find the right tool, the right way to structure your problem, you can solve almost anything.
So it kind of makes you look around and wonder, right? What other magic that you use every single day is really just hiding a simple, brilliant idea like this one?